Hello everyone, welcome back. Today I'm going to talk about Android application security, and it is best practice to secure your Android application while developing or testing Android applications. It's a recommendation in introduction for programmers or for anybody interested in the subject. My name is Yohannes Yemane. I'm a graduate student here in Hallym University, studying legal informatics and forensic science. I'm doing a research on IoT device forensics for past year. Before this, I have been working as a developer. It's either on desktop or Android applications. And also I have an experience on Android overall reverse engineering. So the agendas are this. So I will start with the introduction about the Android application and the Android I will start with the recommendation, the introduction about the Android application, and so I will start with Android application security, and then I will talk about the top application security testers, and I will conclude the overall talk. So as a motivation, as an Android application developer, I know some of the practice of the security practice, so I should know of the security practice of the Android application, and I also work as a reverse engineer, so I face different security challenges while I face these Android applications and other applications. So I thought sharing it could be a good idea, so I hope it gives you the basics and develop from it. I'm by no means an expert on this thing, so I try to develop my knowledge on it, and from the security and from the reverse engineering perspective. Introduction. Android applications are like becoming big part of our lives. It entertains us, it keeps us in touch with our families. We can control our smart homes with them, and sharing anything we want about our lives with the world and so on. So Android dominates the market with around 87% of the market, and while iOS comes a distant second with 12%. As of April 2018, there are around 8.5 million applications on Play Store, and thousands of new applications are added to the marketplace each day. That means that Android application takes a larger share of the market. So even if thousands of applications added to the Android store, and there is a big concern about the application, the security of each application. Most Android applications fail basic security testing. I know it's old statistics, but the around 75 applications fail basic security tests. The application could be like the social medias, the e-commerce applications, and so on. So every enterprise or private like individual developer should consider while developing, consider the security part while developing the apps. But as we know, there is no 100% security unless the application is unreleased or it's not done yet. Uh, that does mean that we shouldn't make the attackers job harder. So we can make it harder by like incorporating basic security methods, so that could make it harder for the attacker. Factors why apps are more secured. The first factor is we might focus on the developing apps, not like the security part of the applications. Like we focus on developing and releasing the function or the application to the users. So we focus on the development part, not the security part. The second is not as development cycle, it's not fully integrated with development stage, or now there is like DevSecOps, now it's coming to the market, but we are not focused, we are not into, we didn't introduce the subject to the development cycle. And the other is lack of quality assurance in testing. And developers also like make error while developing the application, like accidental code errors. This could affect the security of the application, could be also a vulnerability. Like hard coding the passwords, like hashes, not using secured communication are some of the errors. So we can name a lot of factors other than this, but this is the most one. Android app security practices. So this is just a recommended practice for developing a secure Android applications. That doesn't mean that it's only these methods. So let's see some of them. I selected these 6 like security-based security practice like to incorporate in your application while developing it. So the first is root and custom ROM detection. The idea is denying an application from running on rooted device or custom installed ROM devices. As you know, a rooted device gives a root privilege, a root privilege for attacker, and almost all hacking starts with the root privilege. And the second one is anti-emulator. It's protecting the application from running on the emulator. So running an application in emulator gives the attacker powerful way to monitor or manipulate the application. And the third one is anti-debugging. As you know, developers should like disable debugging capability of the application while they release or they post it on Google Store. So but there is a ways like to disable it, to enable it back again. So we have to make sure that the attacker didn't make it, didn't enable it, or so the fourth one is tamper detection. It's detecting if the application is changed or modified. It could be like on or runtime, or it could be like statically. And the phase one is anti-reverse engineering. Attacking starts with reverse engineering. Like most of the time, it starts reversing the application and knowing what the application is doing and searching any hashes or passwords or any strings. It starts with reverse engineering. So we have to protect our codes and our application from reverse engineering. The last one is I selected like SSL or certificate pinning. It is protecting the application not to accept every like certificate they get from the device or from. It can protect it if we pin the application. it can protect the application from man-in-the-middle attacks. So I will start with ROM or root detection method. So the goal is to deny the application running on a rooted device. It's highly effective on its. It's not highly effective on its own, but it can improve the overall application security. It is like it protects also basic attacking methods such as sniffing, man-in-the-middle, Wi-Fi attacking, and so on. Because most of the hacking apps and methodologies requires a rooted device before everything. So first we have to detect for the custom ROM detection for the custom ROM or for rooted device. And common detection methods on like to detect the root if the device is rooted or it is installed the custom ROM, is that we have to first check if there is some kind of apps or package installed on the rooted device, like files such as superuser, demo, and king roots or busybox are used to root the device or to communicate with the root device. So the first method is to check if the install package found on the root device, and the second one is check existing commands or running processes. So like if on the root devices you can get a specific running process like supersu and demo or any other. So we can check the running processes and check if the device is rooted or not. And the third is like the safety net. This is an Android API that creates a profile of the device using software and hardware information. So it then compares against the whitelist device modules that passed the Android compatibility test. So we can check the safety net of the device. So after that we can say that this device is rooted or not. So this is the code, like it's code snippet. So it checks the running process and says yeah, it's rooted or not. So first it lists or gets the running services, then check if there is supersu or super user on the list of the running process. So if it gets as a startup, you can check this. You can use this code to check if the device is like rooted or not. And the second recommended like application security practice is emulator detection. The goal is to deny the application not to run on the emulator. Like make root emulation running the application on the emulation makes the attacker or reverse engineer's jobs harder to use methods to attack the applications. Like if it is your application and somebody else is running the application on the emulator, like we can suspect that the attacker is or someone else is interested in your application. So we have to check the root emulator detection. So the common detection methods are like the first one is to check the Bluetooth. We cannot get like Bluetooth devices on the emulators. So if the device doesn't have the Bluetooth device, we can suspect that it is an emulator. So we can check the Bluetooth device in the device. The second one is checking check indicators and signature of the device. So emulator have their own signature in like names and indicators. Like if the fingerprints or the module contains Google SDK or emulator or generic, we can suspect that it's an emulator. So so we can protect our application from the emulator. Mind that these methods also can be bypassed with hooking or rebuilding the application. So it's just a recommendation. And the third method is check the indicator and signature of the device, like using the telephony manager. The telephony manager returns like the device ID, that is IMEI number, and other values. Based on the returned value, if the IME number is 00 or zeros, so you can say that the device is an emulator. So certified devices have their own unique device ID. So checking this ID also can be used to distinguish the device, the real device, from the emulator. And the third method is anti-debugging method. So debugging is the best way to analyze the runtime behavior of an application. Like debugging allows like stopping through the code, analyze and see the values of the variables, and read and modify values and memory values and so on. So it gives like a room for the attacker to use. So there are two types of debugging methods on Android application. The first method is Java debug wire protocol, and the second is native level ptrace based method. So developers need to implement defensive method against these debugging capabilities. So the common anti-debugging methods are checking the debuggable flag in the application info. Like we can check Android or debuggable attribute in the application info. If the application is connected or if the application is connected to a debugging, if it is debuggable, this value is set. So we can suspect that the application is in debug mode. So using this code, like it returns is if the debugging capability of the application is true or not. So if it is true, the application is on debugging mode, so we can stop the application from debugging at runtime. The second one is checking whether the debugging is currently connected or not. So debug system class has a static class to check it, like return is debuggable connected, returns true if the application is connected to a debugging capability. And the mostly used security practices to protect your codes or your resources from anti-reverse engineering. Reverse engineering is recreating the application and its resources back to where it starts. So that means taking the compiled app and recreate its source code is a reverse engineering. Reverse engineering gives the attacker the opportunity to analyze and the structure, the resource, and its behavior, and helps the attacker to know how the application works and how the application operates. So the APK files is just a RAR file. It's like compressed file. So if we can unzip it, we can get all the resources and other things. So we can just use WRAR to unzip it, or we can use tools like Epicode tools to extract also the applications. Then the Java class or the Dex class can be decompiled to Java code or to Somali code. I don't know if you can see or not, but this is the the application that is not protected or anything. You can see the variable names clear and smooth, and you can see the class names and the structure of the code. So unprotected or unobfuscated code looks like this. So the first method is to protect from reverse engineers, to obfuscate the overall application. So obfuscation is transforming the code and the data to make it more difficult to understand. Like it makes the reverse engineers to understand. It makes the reverse engineers' job harder, right? At least. So obfuscation can be done in various ways, like renaming all variables class names so that they are garbage, flattering the directory of the structure, moving meta names between files, adding garbage codes in the middle of the code, and changing strings to its hex array or equivalent. So there is a lot of ways to obfuscate the source code of the application. And ProGuard is also the obfuscation tool used in Android projects. So it's a plugin in the Android project. You can enable it and use it. So after obfuscation, you can see that this is the original code, and it has all the names and the variables. After obfuscation, you can see that it seems like garbage for anyone who sees this. So obfuscating the code turns this code to this one. At least this is the basic one. So using this, the basic one, is also difficult to understand. As per White Hat Security, they reported the application security statistics report in 2017, and the second most security problem is lack of basic obfuscation. Like it takes around 80% of the attacking. So most of the application lacks this basic obfuscation. So it's recommended to obfuscate before releasing the application. And tamper detection. Tampering used to affect the behavior of the application at runtime or manually changing the source code. So it changes the actual app and its environment. So detecting and preventing it is fundamental for app securities. So preventing tampering also can prevent other security problems like Ssl pinning. With tampering, you can disable Ssl pinning or anti-emulator checks and root detections, so on. So preventing tampering also can protect your application if you incorporate like anti-Ssl pinning and anti-root detections. So by tampering, I mean like hooking and binary patching. So what is how we can prevent binary patching? As a process of changing the compiled apps and inserting code in it, and after that you can reassembling it so that we can get our what we want from the application. As I told you, tampering is one of the methods to bypass Ssl pinning or root and emulator detections. So we have to prevent our application from tampering. Ways to protect and detect it. The first method is to check the SRC or the checksum of the class.dx. So we have, when we release application, we have the code part, the DX part. So we know the SRC or the checksum of that application. So at runtime, we can check the running process and our original class.dx file. So if the SRC is not the same, you know that there is something wrong with the code, or the code is modified. So we can check the SRC of the class.x or the code of the application. And most of the time, anti-emulator or anti-debugging techniques also can be used to detect tampering, because it starts all with debugging techniques and also with root detections, because most the tampering methods needs, I think, the root privilege. And the other one is hooking. So it's a powerful way to monitor or explore or modify apps at runtime without even decompiling or reversing the applications, decompiling the applications without touching the running applications. So Frida and exposed are widely used for this purpose. So exposed can change the behavior of the application at runtime, and it allows also to develop third-party add-ons or modules for the application for the exposed. Most of the time it is used to bypass Ssl pinning, emulator, and root detections. The other framework is Frida. It injects your own script into your running black box process. Then you can hook any function like cryptos, APIs, hashes, and every other thing you want. But it's getting harder after Android N or Android 7.x and above. So thus the two frameworks are making hooking easy on Android applications. I don't know if you can see it, but this is the expose module that hooks the running applications and see everything, what's going on inside the application. So you can see what is writing to SQLite. You can see the shared preference, serialization, cryptos, and the web view also. So with hooking, we can see the attacker can see what's going on in the application and analyze the applications. So how to detect and block it? The easiest one is to check if there is installed package, like the exposed method package are installed on the applications. So we can get all the running process and check if there is exposed in it. Then we can say that someone is trying to detect to hook our applications and block our application. The second method is to check the stack trace for suspicious methods. Researching what kind of track trace we can get when there is a hooking framework or not, then detect the trace to block or kill your application can be a good way to prevent your application from hooking. So check the stack traces while the expose is running or while it's not running. Then differentiate what kind of traces are running while the expose and the Frida are running. Then you can kill your application after if you get the stack traces. And the other one is anti-debugging and root detection methods can also be used to detect if it is if there is hooking in your device. So thus to the Frida and expose needs, I think, the root privilege on the device, and also they need debugging methodology, I think. So detecting also anti-debugging and root detection can be used to protect your application from hooking. So the last one is Ssl pinning. Making your application to exchange information using SSL or HTTPS is a halfway to protect your applications. So that means you can accept every certificate. If there is legit certificate in your device, you can accept that certificate. But the users can also install custom certificates. So that can also lead us to the attack, to man-in-the-middle attack. So SSL certificate or SSL pinning is a solution for this problem. Like the app trust certificate stored on the device, or its own only its own certificates. Like if your application is on if the Amazon application is connecting to the Amazon web server, it only checks the Amazon certificate. If there is any other certificate on the device, they will kill the application. So they are not communicating anything on that communication. So how can we pin it? And after Android N, there is a newer technique, like you can provide your own hash or public keys, including in backup keys in the applications. Like there is network security config XMLs in the XML on the resource of the applications. Then you can pin your hash to 56 public key in it. Then whenever there is another hash or there is another certificate on the application will not communicate or it kill itself. So this is the first one after Android N. And before Android N, we can use the HSpace URL connection to trust a specific set of certificate authorities. So if we get another, if the certificate is other than this trusted set of certificate authorities, we can kill our application. Lastly, using the third party like OKHTTP, we can pin our certificate. As you can see this, we can add our certificate in it. Then our application will check if the certificate is legit or not. So you can read this links if you want to know this about these methods. So at last, I have tried to test applications, like one way or the other way I get in touch with these applications. So I try to test this application based on the criteria I talked earlier. So those are IoT app securities, like IoT application, Android application. So Amazon Alexa, SmartThings, MotherSense, Xiaomi Mi Home applications, and Nest. I select this application. As you know, most of them use Ssl Pinning, except Nest and MotherSense. All of them doesn't detect the root detection, rooted device, and all of them doesn't detect if the device is emulator or not. And this MotherSense, Xiaomi, and Nest applications, like they don't even try the basic obfuscation method. All of them doesn't detect tampering. Like you can insert in the your code in it and rebuild it, and then you can do whatever you want. But most of them use, except the Mother and Nest, they use a Ssl Pinning. So I try to test based on these criteria. So by reverse engineering, I mean like the obfuscation methods, like this reverse engineering, I mean the obfuscations. Anti-tampering method, I used like the static method, maybe like manual methods, like inserting some kind of log method code in the Smalley code and rebuild it and run it. So, and also sometimes I use the expose and Frida. So I use dynamic or static security testing methods, and these are the South Korean apps like I tried to test, and I selected Kakao Talk and the Hallym University, the one where because I'm here, and Nugu and Gigajini. These two are like the speaker applications, and this is the social networking applications. This is the university's application. So the Kakao Talk, they pin there as Ssl, so it's not you can't attack on the middle, and they also obfuscate their applications. And the Hallym, yeah, it's not that much secured. And the Gigajini is like the hardest one. Like they detect roots, they detect if the application is running on the emulator and their code is also obfuscated. Anti-tampering, I didn't try it. And the Ssl pinning, I think partially it works. Sometimes it works, sometimes it's not. I'm not 100% sure, but sometimes it works. So those are the application I tested with this security recommended security practice. As a conclusion, we saw selected Android application security practices, and developer for sure should consider as much security as possible, possible. At least it is better to have to incorporate the recommended security and make it harder for an attacker, even if there is no 100% security on the applications. Ssl pinning is becoming popular, so every big companies are using Ssl pinning to protect their application from man-in-the-middle and other attacks. And as I showed you, lack of basic obfuscation is the second most security problem on the applications. Thank you. This is me. If you have any question, you can find me on these things. Thank you.